Okay, let's move on with group theory and symmetry. So in the last class, we have started to apply symmetry to orbitals. And we have seen that within a particular point group, certain orbitals have certain symmetry types. So for instance, the 2s orbital in the H2O has A1 symmetry, the 2pz orbital also, the 2px has B1 symmetry, and the 2py has B2 symmetry. Now, group theory is even more powerful than just predicting the symmetry types of orbitals. It can actually predict the symmetry type of any mathematical function in a particular point group. So recall, orbitals are mathematical functions because they are wave functions. And if you remember, the px orbital was only a linear function of x. The py orbital was only a function of y. The pz orbital was only a linear function of z. Okay, the 2s orbital was not dependent on any coordinate, and therefore a 2s orbital is spherical. Okay. So for that reason, we could have just derived the same information, meaning the symmetry type of the orbital in the particular point group from the mathematical form of the respective orbital. Okay? So because the px orbital is a linear function of x, we know that its symmetry type must be B1. Because the 2py orbital is a linear function of y, we know it needs to be of symmetry type B2. Because the pz orbital is a linear function of z, it needs to have symmetry type A1, and an s orbital in any point group always has the totally symmetric symmetry type, which is A1 in the point group C2V. Okay, now we can expand our considerations also to other orbitals. So the oxygen also has d orbitals. They're not occupied, but they still exist in the atom. So we can ask, well, what are the symmetry types of these orbitals in the point group C2V? Okay, now here you see the dz square orbital, and we can again ask, well, how do the symmetry operations change that orbital in order to determine the symmetry type? Okay, now as we carry out the identity, the orbital will not change. As we carry out the C2 symmetry operation, and we will rotate around this axis here, and we see that this won't change our orbital. Now, if we apply the sigma v operation, this will also not change the orbital because the sigma v is in the plane of the molecule. And the same is true for the sigma v prime. So this means that the symmetry type is A1. So now what about this orbital here, which is the dxz orbital? So applying the identity never changes anything. But now we see when we carry out the C2 symmetry operation, that then these two lobes are being swapped up. So they have different algebraic signs. So that means that the orbital changes algebraic sign. The same is true for this, for these two lobes as well. Okay. Now, when we look at the XZ mirror plane, we see that this does nothing with that orbital. But when we apply the YZ mirror plane, then this does flip the algebraic signs again. Okay, because the YZ mirror plane stands here. So again, these two lobes are getting swapped up and these two lobes are getting swapped up, and these pairs of lobes have different algebraic sign. So that means that overall we have B1 symmetry for E and sigma XZ, the characters are 1, and for C2 and sigma YZ, the characters are -1. Okay, then we have here the x square minus y square orbital. Now what about this one? When we apply the identity, well, certainly nothing will change. When we apply the C2 symmetry operation, you see also nothing changes because it swaps up these two lobes, which have the same algebraic sign, and swaps up these two lobes, which also have the same algebraic sign. Okay, when we apply the sigma XZ, we see, well, it swaps up these two, which have the same algebraic sign, and these two blue lobes here, they remain in their position. Okay? So the character for the sigma XZ should also be +1. Now, what about YZ? Well, the YZ mirror plane stands here, so in this case, that swaps up these two, but they have the same algebraic sign, and these two lobes here remain in their position. So that means overall, the 3D x square minus y square orbital has also a 1 symmetry. Okay, now let us look at the dyz, which you see here. So the identity never changes anything. What about the C2? Well, you see the C2 actually rotates the blue lobe, which is in the back here, to the front, and that orange lobe to the back. And here at the bottom, this orange lobe here will be moved to the front, and the blue lobe here will be moved to the back. Okay, so that means the algebraic sign of the wave function changes, and the character in the irreducible representation should be -1. Okay. Now that means that the symmetry of this orbital should be actually B2. Okay. If that is so, then if we carry out the sigma YZ mirror plane, the algebraic sign should not change. We can verify that. So the sigma YZ is here. So you see that in this case, no lobe changes its position. And that means that the algebraic sign of the wave function doesn't change. You verified that the 3D YZ orbital has the symmetry type B2. So last but not least, we have to consider this one. So this is the 3D XY. Remember, the 3D XY is rotated by 45 degrees relative to the 3D x square minus y square. So it has its lobes actually in between the x and the y axis, whereas the 3D x square minus y square has the lobes on the axis. Let's apply the symmetry operations. So the identity never does anything. What about the C2? So the C2 rotates everything around 180 degrees. And you see that moves this lobe here into this position and this blue lobe here into that position. So the algebraic sign doesn't change. Okay. So therefore, well, we should have an A-type symmetry type. So what about the dxc? So this is the mirror plane, which is in the plane of the molecule. So you can see that when we carry out the symmetry operation, these two lobes are being swapped up and they have different algebraic sign. And these two lobes here are also swapped up and also have different algebraic sign. So that means the character should be -1 in the irreducible representation. So now what about the sigma yz? The sigma yz stands here. And you see that in this case, these two lobes are being swapped up, which have different algebraic sign. And these two lobes here are also being swapped up, having different algebraic sign. And therefore, the character should also be -1. So now you see that this corresponds to a symmetry type that we have not considered before. And this is the A2 symmetry type, okay, which has the characters 1, 1, -1, -1. Okay, so no coordinate does belong to that symmetry type, but there can still be mathematical functions, such as the mathematical function for the 3D xy orbital that belongs to the symmetry type. Okay, so now that raises the questions. Well, how many symmetry types can there be for any mathematical function? And the answer is that depends on the point group. And the for the point group C2V, it's exactly these 4 symmetry types: A1, A2, B1, and B2. And that means that any mathematical function must belong to these 4 symmetry types. Okay, so now a complete set of irreducible representations for a specific point group constitutes what is called a character table. And you see here the complete character table for the point group C2V. So let us analyze the character table in a little bit more detail. And now I'm just switching the screen. You see here again the character table for the point group C2V, just like we saw before. And let's go through that character table systematically to understand all its properties. So you see that there are several columns. So here in the first column, you see the point group symbol, in this case C2V. And below that, you see all the different symmetry types for the irreducible representations that this particular point group can have. Like we said before, for C2V, that's A1, A2, B1, and B2. And then you see here several columns. And in these columns, we see all the symmetry operations that are conjugate. And symmetry operations that are conjugate are grouped in a so-called class. So class means nothing else but a column. So in the case of the point of C2V, all the different symmetry operations are in their own class. Okay, so that means that none of the 4 symmetry operations are conjugate relative to each other. So we have previously already qualitatively said that conjugate symmetry operations perform symmetry operations analogously. Okay. Here we get a more precise definition of what conjugate means. Conjugate means that 2 symmetry operations need to have the same characters in the irreducible representation to be in the same class. You see that for the force symmetry operation in the C2V point group, this is not the case. So therefore, each symmetry operation gets its own column, meaning its own class. See that the sets of irreducible representations, the characters for the irreducible representations are all different. Okay, for the identity, they're all 1. For C2, we have 1, 1, minus 1, minus 1. For sigma, we have 1, minus 1, 1, minus 1. And for sigma V prime, we have 1, minus 1, minus 1. 1. Okay, then you see further to the right, in two other columns, the different mathematical functions that are belonging to the different irreducible representations. So one column is for linear functions, and another column is for square functions. The coordinates, or simple coordinates, are considered linear functions. And you see here the coordinates z, x, and y in the rows for the irreducible representations belonging to the symmetry type A1, B1, and B2, respectively. So that means that these coordinates z, x, and y have symmetry types A1, B1, and B2, respectively, but generally spoken, any mathematical function, which is a linear function of z, x, or y, have the symmetry types A1, B1, and B2, respectively, and orbitals belong to that. This is why, as we discussed before, the 2pz orbital has the symmetry type A1, the 2px orbital has the symmetry type B1, and the 2py orbital has the symmetry type B2. So you see that in addition to the coordinates x, y, z, you see also three other symbols, rz, ry, and rx. So these symbols relate to rotations around a particular axis. So a vector can not only be linear, it can also be a rotational vector. And these rotational vectors also belong to certain symmetry types, depending on which axis we rotate. So for instance, rotation around the z-axis is associated with symmetry type A2, which is associated with the characters 1, 1, minus 1, and minus 1 in the associated irreducible representation. So is there a way we can understand that a rotational vector that rotates around z has that symmetry type? The answer is yes, and I want to show you briefly how this works. So you see here a rotational vector, which in this case rotates clockwise, and we rotate around an axis z, which stands here. So now we need to see, well, what do the symmetry operations do with this vector? As we carry out the symmetry operation, does the direction of the vector change or not? Okay, so now the identity never does anything. So therefore, the vector will still rotate clockwise. Now, what about C2? So now if we rotate this vector by 180 degrees, then it will look like this. Yeah. So has it changed its direction, or does it still rotate clockwise? Can anybody answer that?
It looks like it's still rotating clockwise.
Yeah, correct. So it's still rotating clockwise. So therefore, it should be associated with the character +1 in the irreducible representation. Yeah? And you see that this is the case for the A2 symmetry type. Okay, this character here. So now what about the other two remaining symmetry operations? So what about sigma rho? So if we apply sigma rho, then we mirror this vector which rotates around C at a mirror plane which is within the paper plane. Okay, so that basically mirrors this part here to the back and this part here to the front. Okay, and after we have carried out the symmetry operation, our vector, rotational vector, looks like this. So now, does it still rotate in the same direction, or does it rotate in the different direction?
It's rotating in the opposite direction.
Correct. So now we see it's rotating counterclockwise, and therefore it's associated with a symbol of -1 in the irreducible representation. Okay. Now the same happens when we carry out the sigma v symmetry operation. So if we mirror this vector here, then it will look like this, and you see that after that it rotates counterclockwise. Okay, so this is how I can understand why rotation around C is associated with the symmetry type A2. Okay, we could do the same with rotation around Y and X, and we would find that rotation around Y is associated with a B1 symmetry type, and rotation around X associated with a B2 symmetry type. Okay. So last but not least, here you see in the last column square functions, and also mathematical square functions are associated with the symmetry type, a certain symmetry type. Okay, some orbitals are square functions. Okay, so for example, a dxy orbital is a function of the coordinate x times the coordinate y. And therefore, we can easily read from the character table that it's belonging to the symmetry type A2. We previously determined this manually by inspection on the previous slide, but a great use of a character table is that it directly tells you, well, what is the symmetry type of a particular orbital, and you don't have to derive that. Okay? So similar, any mathematical function with the product of x times y would belong symmetry type B1, therefore a dxc orbital would belong to the symmetry type B1, and one can easily read that from a character table. Any mathematical function with the product of y times z, such a dyz orbital, belong to a symmetry type B2. So any mathematical function that would be a function of x squared, y squared, or z squared would belong to the symmetry type A1. From that, we would understand that the dz square orbital would belong to the symmetry type A1. All right. So a few more things to consider. From a character table, we can also easily derive the order of a point group, because the number of symmetry operations gives the order of the point group. So in this case, we would need to look how many symmetry operations can we actually see in this part of the character table. So it's just 1, 2, 3, 4. Okay. So now the sum of the characters under this symmetry operation E here defines the dimension of the point group. So the dimension of the point group in this case would also be 4. 1, 2, 3, 4. Okay. So another property of a point group is that its character table has one totally symmetric irreducible representation in which all characters are +1. In the point group C2V, this is the A1 type irreducible representation, and you can see that its characters are all +1, and this irreducible representation is always listed first in the character table. All right, so thus far, things were relatively simple because thus far, we have only looked at molecules in which coordinates were independent from each other. Now let us look at matrix representations of symmetry operations and the associated character tables in which this is no longer the case. So for example, in the point group C3, you will see that in such a point group, certain coordinates can be dependent from each other. We can say there are degenerate, and as a result of that, the matrix representations of the symmetry operations will not be as simple as we saw before for the example of the H2O molecule in the point group C2E, but more complicated. And also the character tables deriving from that are somewhat more complicated to understand. So let us approach this rationally and systematically. So for instance, the ammonia molecule, NH3, belongs to the point group C3b. What are the symmetry operations and how can we represent these symmetry operations by matrices? So first of all, we should define the coordinate system in a useful way. We can have the x-axis pointing to this direction and the y-axis pointing upwards. And we can orient the NH3 molecule so that, well, the z-axis goes through the top of the pyramid, this nitrogen atom here, and one NH bond, this one here, lies within the XZ plane. Okay. So now this makes this NH bond point to the front and this NH bond point to the back. Okay. So now in this case, we have a principal axis of the order 3, a C3 axis, and the C3 axis rotates around the Z axis. So now let us consider how the coordinates are being transformed as we carry out such a symmetry operation. Okay, let us look at the molecule from the bird's perspective. Okay, so in the bird's perspective, the x-axis will still point to the right. Okay, but now the y-axis will point to the top and the z-axis would point directly toward us. Okay, so now let us consider a particular point within the xy plane, which has the coordinates x and y respectively. Okay, so this point would be represented by a vector which would point from the origin to that particular point. So now let us rotate around the z-axis, and first let us rotate by an arbitrary angle theta. Okay? So now as we rotate around an arbitrary angle theta, well, the coordinate x will be transformed into a new coordinate x prime, and the old coordinate y will be transformed into a new coordinate y prime. So you see that in contrast to a C2 rotation, when we rotate around an arbitrary angle, now the change of the coordinate x also implies a change of a coordinate y. Therefore, the coordinates x and y are no longer independent. They transform dependently from on each other. So now, how exactly do they transform? And that can be described by trigonometry. So according to trigonometry, the new coordinate x prime will be the old coordinate x times cosinus theta minus y times sinus theta. And the new coordinate y prime will be x times sinus theta plus y times cosinus theta. Okay, so also from these formulas, you see that x and y are now dependent from each other because x prime will not only depend on x, but also on y, and y prime, the new coordinate y, will not only depend on y, but also depend on x. Okay, so now, how could we describe the C3 symmetry operation, or more general, a rotation of the general angle theta, using a matrix? What would be the matrix representation of that symmetry operation? Well, the matrix representation of that rotation operation would need to have the property that when multiplied with the matrix of the old coordinates gives the new coordinates, the matrix of the new coordinates. Now the old coordinates are just x, y, z, and we just determine what the new coordinates are. And the new coordinates are, well, x times cosinus theta minus y times sinus theta, x times sinus theta plus y times cosinus theta. Well, what will be the change for the coordinate z? Well, there will be no change. Therefore, the new coordinate should also be z. And I see that this is actually a mistake here, because that should not be a 1, but it should actually be a z. I don't know why this is a 1. Okay. So now, what would be that matrix that when multiplied with the old coordinates gives the new coordinates? The matrix would have this form here: cosinus theta minus sinus theta 0, sinus theta, cosinus theta 0, and 0, 0, 1. We could again verify with using the multiplication rules for matrices that when this matrix is multiplied with this matrix, this gives that matrix. I do not do this explicitly. Here you can do this as an additional homework if you want to verify this by yourself and if you want to convince yourself. So now, what would be the next step? Well, the next step would be that we apply this more general problem to the C3 rotational axis in the point group C3V. So now, for the C31 and C32, theta is 120 and 240 degrees, respectively. So now the sinus theta of 120 degrees is minus the square root of 3/2. The sinus of 240 degrees is the square root of 3/2. So the cosinus of 120 degrees is minus 1/2, and the cosinus of 240 degrees is also minus 1/2. Okay, so now we can just plug in these values into the matrix, the more general matrix that we previously derived, and then, considering that these are the values for the clockwise rotation, and by definition we always rotate counterclockwise, the C32 will have the form minus 1/2 minus the square root of 3/2, 0, the square root of 3/2 minus 1/2, 0, and 0, 0, 1. So the C31 will have the form minus 1/2, the square root of 3/2, 0, the square root of 3/2 minus 1/2, 0, and 0, 0, 1. Now you see that these matrices look somewhat different than the matrices that we have seen for the point group C2V. In the point group C2V, we only had non-integer values on the trace of the matrices. And you see that's now no longer the case. We have also non-zero entries which are not on the trace of the matrix. And that's essentially caused by the dependency of the two coordinates x and y. We can also say about the degeneracy of the coordinates x and y. So now, in the point of C3V, we have more symmetry operations to consider. Okay. We also have mirror planes. In fact, we have 3 vertical mirror planes. And the 3 vertical mirror planes go through the 3 NH bonds. Okay, here, and here, and here. So now we see that one NH bond lies within the XZ plane. Okay, therefore, the development of the matrix representation for that mirror plane is pretty straightforward. Okay, it is 1, 0, 0, 0, minus 1, 0, and 0, 0, 1. So why is that? Because within the XZ plane, well, because we mirror at the XZ plane, the coordinates x and z will not change. Okay, and any coordinate y will just reverse its algebraic sign. Okay, so any point that lies below the mirror plane, okay, will be mirrored well to the front of the mirror plane. And any point in space that lies well before the XZ mirror plane will be mirrored below. Okay, that doesn't change the coordinates x and z, but the y coordinate changes algebraic sign. So now the situation is more complicated for the other 2 mirror planes, because the other 2 mirror planes do not coincide with a mirror plane that is produced by 2 coordinates. Okay, therefore again, the x and the y coordinate will be, well, dependent on each other. And for that reason, the matrices will look more complicated. I'm not deriving this in detail. I'm just qualitatively describing this just so that you're not losing the overview over the big picture and the big story that I want to tell you. So for the second mirror plane, the matrix is a half minus the square root of 3 over 2, 0, minus the square root of 3 over 2, minus a half, 0, 0, 0, 1. And for the third mirror plane, we have this matrix here as the matrix representation of the symmetry operation. So keep in mind, though, that in the point of C3V, all the mirror planes are being conjugate relative to each other. And we see this also in a moment in the character table associated with the point group C3V. All right, so now finally we need to look at the identity also. Well, the identity never changes any coordinates, so it has always the form 1, 0, 0, 0, 1, 0, and 0, 0, 1. So now we have found all the transformation matrices for the symmetry operations. We can now derive the character table from these matrices. So you see here the entire character table for the point group C3 V. So let us systematically go through that character table as well in order to understand it. So now, like before, to the very left, you see the point group symbol and the symmetry types that exist within that point group. So now to the right, you see the different columns, classes for the different symmetry operations that are conjugate. You see here the identity. You see here we have the 2C3 symmetry operations, which are now in the same class because they are conjugate. Okay? That means that they have the same characters in their respective irreducible representations. Because of that, we can say that they perform similarly, analogously, equivalently. And we have here the 3 sigma V symmetry operations, which are also grouped together within one column, meaning that they belong to the same class. Also, they have the same characters in the irreducible representations. All right. Then you see here the different symmetry types that we have. So we have here the A1 symmetry type. We have here an A2 symmetry type. And here we have an E symmetry type. So that E symmetry type is something new. Previously, we only had symmetry types which are not degenerate. Here we have a symmetry type which is double degenerate. That means this symmetry type is associated with the coordinates that are dependent on each other. We can also say they are double degenerate. So in this case, this is the two coordinates x and y. They are degenerate, and therefore they are being grouped together by parentheses here, indicating that they are degenerate. There are also other mathematical functions that are dependent from each other and are degenerate. For example, x squared minus y squared and dxy are degenerate, and xz and yz are also degenerate. Okay, yeah, this is just what I explained. So now you see here unusual characters in that irreducible representation of the type E. So we have here a 2 entry, okay, which we don't really understand yet. We have here a 0 entry, which we don't really understand yet. So far, we have had only entries in which the characters were either +1 or -1. So these unusual numbers are now associated again with the degeneracy, and you can derive them the following way. And now you need to look at the matrix representations of the symmetry operations. So we saw that, well, we had the matrix for the identity, which was this one here. So here we had the matrix for the C2 and C3 symmetry operations in its general form. And you see here one of the 3 matrices for the 3 sigma V symmetry operations. We have chosen here the most simple one, but we could also choose the other 2. It wouldn't matter. Okay. So now, because of the double degeneracy of x and y, the character in the irreducible representation associated with E is now the sum of the characters of the on the trace of the matrix. Okay, so now for the identity, this is 1 plus 1, and that gives 2. Okay, now what about the C3? Well, we saw previously that for a 120-degree rotation, the values on the trace of the matrix become a -0.5 and -0.5 respectively. So -0.5 plus -0.5, well, that gives -1, and that explains this character here. So now, last but not least, we see here that for the sigma v's, the sum of the trace of the matrix is plus 1 plus -1, well, and that gives 0, and that explains this 0 here. Okay. So now what about the z coordinate? So the z coordinate is not dependent on any other coordinate. Therefore, well, the character for its irreducible representation are 1, 1, and 1. And that's in this case the symmetry type A1. You see that, well, the z coordinate is also listed here for this symmetry type, because generally any linear function of C will not change upon the execution of the symmetry operations E, C3, and sigma V, respectively. Okay, you see again that in the character table for the point group C3V, there is an irreducible representation which is not associated with any coordinate, and that's the symmetry type A2. But certain mathematical functions are associated with the symmetry type A2 in the point group C3V. In this case, it's the rotation around C. Okay, but any mathematical function would either have the symmetry type A1, A2, or E. Okay. Now, in addition to a double degeneracy, which is indicated by a simple E in the character table, you can also have a triple degeneracy indicated by a simple T. And that would mean that all three coordinates in space, X, Y, and Z, are dependent on each other. They are a triple degenerate. So for both the symbols E and T, there can be, again, subscripts and superscripts. And we do not need to know them all and memorize them all. I just want to illustrate this concept by giving a few examples here. So you can, for instance, have primes. One prime and a double prime would mean that the symmetry representation that this would indicate symmetric or antisymmetric situations with respect to sigma h. Okay, so if you have a sigma h present and your wave function, for instance, wouldn't change its algebraic sign upon applying the symmetry operation, then it would be E prime. If it was antisymmetric and the algebraic sign would change, then it would be of E prime prime. We can also have subscripts like gerade and ungerade, for example. So gerade would mean symmetric with regard to an inversion, and U would mean antisymmetric with regard to an inversion. So for instance, we could have sim type TG, for example, or EU. Okay, I see that we have reached the end of our time, therefore let us stop here.